Okay, good morning. So, got down with node voltage, mesh current. Quiz on mesh current is coming up on Monday. And then we have superposition. The homework is due today. And then the big topic of Thevenin and Norton, which is homework 12. Let's open up Canvas course page. Let's go there. All right, assignments. And then let's see. Yeah, superposition due today, Thevenin Norton due 5 days from today. All right, so what do you all want to discuss today? You want to go over superposition? Any questions about homework 11? Yes. Okay. It did not, you said it did not go well? Okay. As soon as it finished loading. Okay, 2.95 and 2.97. I think, let's see, I think another student asked about 2.97 last class, right? I think we did. Yeah, 2.97. So since this is already on here, let me just ask if anyone has a question about this. Everybody comfortable with this one? This was this mesh current or was this? Sometimes they have the same problems in multiple, asking to solve in multiple ways. So I might have assigned it for mesh current perhaps. Let's see. No, this was superposition, 2.97 superposition. Okay. Since it's already here, I can go ahead and do a quick overview on this. And then we'll look at 2.95. All right, 2.97, we have two current sources, two resistors. Obviously, we can solve, it is possible to solve this via multiple techniques, node voltage, mesh current. We can reduce it down to one single resistance also, but we'll use superposition. So in superposition, we are breaking the circuit into two parts, solve it with IA active, and then solve it with IB active. So in superposition, only one source is active at a time. Okay, only one source is active at a time. So if IA is active, then our circuit looks like this. If IA is active, all the other sources in the circuit must be inactive. To deactivate a current source, we simply remove it from the circuit, replace it with an open source. Open circuit. Voltage sources are replaced with a short circuit. So this would be I1A, and this would be I2A. Now we can apply any technique we want to solve this. Well, the whole point of using superposition is that we only have one source in the circuit, so we can apply series parallel analysis techniques, meaning you combine all the resistors down to one single REQ, and then solve it that way. In this case, we see that there are two resistors in parallel, and we have a current source. So what techniques comes to mind? It's a current, and current is being divided into multiple parts. Current division. And so we can apply current division and find these currents in one step. Important to keep in mind that superposition is a technique where you separate out individual pieces, meaning by just analyzing one source at a time. Once you set up the circuit, then you're free to choose any technique you want. Okay, you can apply Ohm's law, KVL, KCL, current division, voltage division, in any form that you want. Okay, but if it asks for superposition, that means at the very top, you have to show your understanding of superposition. And once you divide up the circuit, then apply any technique. Make sense? Right? And then for IB active, we have the same, except IA is now gone from the picture. It's deactivated and only 2 amp current source is active. Now this is I2B and I2A. Keep in mind that 2 amps current is coming down. And so the currents are actually flowing up. If they're flowing up, then the I1 and I2, because of A and B, are going to be flowing in the opposite direction. And so when you sum up these currents, we have to ensure that we are applying a negative sign to that reference point. See, I1 is given to us as flowing in the downward direction. Okay. These two currents are already given to us as flowing in the downward direction. So any mathematical equation we write must reference this direction. The 2 amp current is flowing down, so it goes up in these two branches. That means we have to take I2A and I2B as minus or negative. Okay. So I2A and I2B must be referenced as negative. Keep that important point in mind when we solve this. All right, let's take a pause. Think over that. Let me know if you have any questions. Yes. So current division is applied. You simply take, if it's I1 for any circuit, and then it's the total source current times the REQ divided by R1. For I2, it would be REQ divided by R2. And REQ is only the resistors that are in parallel for that current, not the entire circuit. Sometimes we have entire circuits where there are some series resistors, multiple resistors, and then there are some parallel resistors where we're trying to find the current being divided. So REQ is restricted only to those resistors, not to the entire circuit. That's, again, a common point of error that I've seen over the years. It's only these two. Okay, any other questions? Yes. 2.95. Yeah, so we'll take a look at 2.95 after this. So if there are no more questions on this one, then we'll move on to 2.95. Okay, right. Let's go to 2.95. Let me copy over the question. Let's do this one. Oh, okay. We saw this circuit in node voltage, right? Node voltage analysis. Okay, so what is the question asking of us? Question is asking solve for IS. R1 is 6 and R3 is 10. All right, let's write it down. What was it? This was 6 ohms, and this was 6, and R3 was 10 ohms, right? 6, 6, and 10, and we're asked to find IS. Okay, all right. So how many sources? Two sources in a circuit. One is a voltage source, the other one's a current source. So let's call this Vs and Is. And let's draw the circuit for Vs active. If Vs is active, what happens to the current source? The current source is deactivated and we remove it from the circuit. So what is left behind in the circuit? And let's call this ISA. And then the other one we'll call ISB. Does this make sense? So what is ISA? Calculate and let me know. Or how would you go about solving this? Forget about calculation. How would you go about solving this? Absolutely. So just because this reference point is shown here, reference point doesn't mean anything in this case. Reference point is just if you're trying to measure voltages at different places in the circuit. If you're trying to find the current through a resistor, it does not matter. Okay. So whether there's a reference point or not, the 6 and the 10 are in series. There is no other connection because for the purposes of this analysis using superposition, the 1 amp current source is open circuit, meaning it's removed from the circuit. And so 6 and 10 are in series, and then that would be in parallel with 6. You find the total REQ, and that would give you the value for IS or ISA. What other point should we note? Current for a source always flows from minus to plus. So ISA is flowing in the opposite direction. So whatever current we find for the source, we have to put a minus in front of it. Simply because it's already given to us in that way. So again, small conceptual pieces in every problem. Okay, so since we simply need to find the total current for the source, the easiest thing to do is to find REQ and apply Ohm's law. We already have Vs as equal to 10 volts. Does that make sense to everyone? Is anyone solving this as we go along? Then I can take a pause. Otherwise, I can move on. Okay. All right, let's look at IS active. And this is interesting. If IS is active, what happens to the voltage source? Okay, what do we replace the voltage source with if you want to deactivate? Short circuit, right? So the current source is kept open, and now we have modified the circuit. So if you modify the circuit, what is happening in that circuit? So IS is coming from here. It's making a right turn, going there. And then what happens? We have R3, we have R2. What happens with that short circuit? Is it what? Yeah. Also, what happens to R1 at the top? So if you have a short circuit, anything that is parallel with a short circuit is effectively redundant, meaning it's not, may as well not be part of the circuit. So this is what happens. We have current coming through. So this current comes through here, right? Now, it can go up here, it can go down there, it can go here, 3 places. But let's say, forget about these two for a minute, okay? Forget about these two for a minute. You have IS coming in, it's trying to go this way, it's trying to go this way. Current will always take the path of the least resistance. So if it's dividing between 6 ohms and the short circuit resistance is 0 ohms. So what happens to IS? Everything is going to go through that short circuit. Nothing will flow through the 6 ohm resistor. The 6 ohm resistor could be very small, like 1 ohm, 0.1 ohm, like really, really small. We can't probably even measure it. But ideal components, if you have 0 and then you have even 0.1, everything is going to go through 0. Nothing is going through 0.1, meaning effectively that resistor is receiving no current. It may as well not be part of the circuit at all. So the concept is, if you have a short circuit wire between any two nodes, anything that is connected between those two nodes is effectively removed from the circuit. And that's the concept that needs to be applied here. And so R1 effectively removed from the circuit because of the short circuit wire. So now where is IS going? So let's take a pause, think over it for a few seconds, and then think about where IS is actually going. At this point, when I was a student, what I would do is, if I apply, so I would take it step by step. So I applied the concept, then I realized, okay, R1 is no longer part of the circuit. Then I would redraw the circuit again, just to, make it make sense in my head. Okay. Now, after all these years, obviously, it just becomes habit, and so we automatically understand. But when I was a student trying to learn it, I would redraw the circuit as many times as I needed until it started to make sense. So if you redraw the circuit, what is left in the circuit? Just 2 resistors, and we have a current source. And what is the relationship between those two resistors? They're in parallel. So you have one current source, you have two resistors. The current source is also in parallel with the resistors. So what technique can we apply? Anyone? Current division. Exactly. So IS comes through, nothing goes through here. We have it splitting. It splits in two. This becomes I2B, and this is the current that flows through R2, which let's call it I1B. And then keep in mind, we are trying to find this current, which is ISB. So we don't even need to find I2B. We simply find I1B, put a minus sign in front of it, and that becomes ISB. And I1B from current division can be found as IS times REQ over R2. Let's take a pause. Let me know if you have any questions. Does current division only work when there are two branches? What? Oh, it could be multiple resistors in parallel, and we can still apply current division. So it's the resistor that we're trying to find the current. So if you're trying to find the current for, like, say, R3, then we put R3 in the denominator. We find the current for R2, then R2 is in the denominator. That's the resistor of interest. Did that answer all your questions? Okay, any other questions? No other questions. I will move on. Okay. How many of you have started on homework 12? Anyone yet? How many have watched the videos on Thevenin Norton? Not yet? Okay. So we had 280, 281, 283, 284. That one is straightforward. This one might be a little tricky. This one is fine, straightforward. This one is okay. Not too. I might talk about this later. Okay. So I'm just going to go over the concept of Thevenin Norton briefly, and then Um, you know, you'll have the weekend, watch the lecture videos, attempt the homework, and you can take a look at the questions and the problems on Monday. But let's see what it is. Okay. So Thevenin, his full name was Leon Charles Thevenin. He was a French commandant. He was a commandant in the French army, but he was a telegraph engineer. He was a French telegraph engineer who was working with a lot of electrical circuits. It was doing some research on linear circuits and linear circuit analysis. And so in the late 1800s, around 1880s, 1890, he postulated a theory stating that if you have a large circuit comprising of a large number of sources and a large number of linear resistors and linear components, then it was possible to represent the entire circuit from the perspective of two terminals. You could represent the entire circuit as one single voltage source in series with resistance. So you have a large circuit, there's multiple voltage sources and current sources present in the circuit, and there are several hundred or thousands of resistors present in the circuit. And what his theory said was you could take all of the sources in that circuit and represent it as one single voltage source. And you could take all of the resistors in that circuit and represent it as one single resistance. And the resistance and the voltage source would be in series. So you'd have a circuit. It's a sealed box. We don't know what's inside the box. Multiple sources, plus minus, current sources, went this way, and then you have resistors, resistors connected randomly. And then we'd have two terminals to access that circuit. Okay. And what Thevenin said was, let's say this is A, this is B. What Thevenin said was you could take this entire sealed box you could take the circuit in a sealed box and you could represent it as a resistor, single resistor in series with a voltage source. Sometimes also drawn out like this. Actually, not sometimes. Pretty much most of the time it's drawn out like this. That voltage source was named after him, came to be known as Thevenin voltage, VTH, and Thevenin resistance, RTH. Okay, VTH and RTH. And that's what his theorem was. And so you're taking a large circuit with an unknown number of sources, components, and you are saying it is equivalent to this one voltage source, hence Thevenin equivalent circuit. It's similar to trying to find REQ for a network of resistors. So you have a large network of resistors, and you have two measurement terminals, and you measure between those two terminals, you get one value. That value is the total equivalent resistance. And so it's the same principle. Okay, one single voltage source to represent all other sources. And all of those sources could be any combination, could be voltage sources, could be current sources, could be voltage and current sources, does not really matter. Okay, so you're representing all of those voltage plus current sources as a single voltage source. Okay, does that make sense to everyone? Okay, so when you watch the lecture videos, you hear me say the same thing. You take a large circuit, you're representing as one single voltage source. And that in short is Thevenin's theorem. This is not a new analysis technique. Okay, Thevenin theorem is not an analysis technique per se. All right, it's an application of all the techniques that we have learned. I mean, just generally speaking, we'll say, okay, it's a Thevenin technique, right? But technically, we are not performing any new, or we are not learning any new circuit analysis techniques. We are still applying the same old techniques that we have learned. In order to find the Thevenin resistance, we find the total Req of the circuit, which is a technique that we've already learned before. Does that make sense to everyone? Right? So RTH is not a new technique. RTH is simply Req as measured between A and B. And that's something that we've already done. VTH, we can find using Ohm's law, KVL, KCL, current division, voltage division, node voltage, mesh current, superposition. Any of the analysis techniques that we have learned previously, we can use to find VTH. Right? You have applied node voltage and mesh current to current sources as well as voltage sources. All we are doing is we are trying to find the voltage between those two terminals. Make sense? Okay. So that's Thevenin equivalent circuit. A few decades later, around the 1920s, there was a American telephone engineer working for Bell Labs. He was working with a lot of audio equipment, and so working with a lot of current sources and current sinks. His name was Edward Norton. Okay. And he postulated his own theory based off of Thevenin's theorem. And he said that we could take this large linear network, and instead of representing with a voltage source, we could represent it as a current source. And so instead of using voltage sources like Thevenin voltage, Thevenin resistance, you could represent the same thing as a single current source between the same terminals. The resistor this time would be in parallel. Still, the value would still be RTH. This current came to be named after him. So Norton current. Sometimes some authors and some researchers, some people like to use RN, the Norton resistance. But the Norton resistance and the Thevenin resistance are exactly the same thing, no difference. Okay. So again, Norton proposed his own theorem that came to be named after him. So it's now known as the Norton equivalent circuit. Basically the same principle, saying you have a large linear circuit comprising of voltage sources and current sources and a lot of other things. You could represent it all with one single current source named Norton current, IN. And the same Req for all the resistors in the network would be the Norton resistance or the Thevenin resistance, RN or RTH. Okay. And that's what it is, Thevenin and Norton. Very important concept in circuit analysis. Okay. All right, let's take a pause. Let me know if you have any questions regarding this principle. I would strongly recommend that if you have time today, like after this class or maybe in the afternoon, review those videos. It's, from our perspective, it seems like a straightforward concept, but from the student's perspective, when you're learning it for the first time, it's tricky and causes issues sometimes. So review it as soon as possible. Okay, any questions? All right. Okay. One final thing I would note about this, and you will see this on the video also, is because we are saying that this large circuit is equal to Thevenin, and this large circuit is equal to Norton. And so if they're both equals, then we can say the Thevenin network for a circuit and the Norton for the same circuit are also equal to each other. And so the relationship between these three quantities can be written as VTH is equal to IN times RTH. Ohm's law relates these three quantities. Okay, so the voltage source in series with the resistor is the same as a current source in parallel with that same resistor. Okay. The theoretical analysis of Thevenin and Norton takes a while because we are performing manual calculations and setting up the circuit and everything. But if you're doing this in the lab, it takes less than 2 minutes. How many of you are taking the lab? Okay, so the lab for next week is Thevenin Norton. You're measuring three quantities: resistance, current, and voltage. No matter what the lab manual tells you to do, what you want to do first is you measure the Thevenin, you measure the current first. Okay, I'll explain. So for the lab, you're going to build a circuit. You'll have the circuit and you have these output terminals. Let's call them A and B. Okay. A and B is where we are calculating or measuring everything, right? So the Thevenin voltage is measured at A and B. The current is also measured at A and B. The resistance is also measured at A and B, right? So you take your meter and you take your meter's two terminals and you connect it directly to A and B. Okay. Once you make that connection at the beginning, you don't need to disconnect it until all three measurements are done. Don't do anything to this. You just take your meter, you connect it to your circuit A and B. Then what you're going to do next is you put it in current measurement mode. So you measure first, you measure IN, next you measure VTH, and third and last, you measure RTH. Okay. And there's a reason for this. So first you measure IN. When you measure current on a meter, what do you have to do? On the meter, you have to take the terminal and you have to switch it manually to the current measurement terminal. So you get that done first. Well, for Norton, what do we need? We need a short circuit wire going from A to B. A meter in current measurement mode is a short circuit wire. So the meter provides a pathway for the current to flow as well as it's doing the measurement. Okay, so keep this in mind when you're doing the lab. You connect the meter, you put it in current measurement mode, turn the power supply on. Whatever current is going through, that's your Norton current. Then once you're done with that measurement, you take the terminal out, put it into voltage measurement, change it to voltage, measure VTH. Whatever voltage is coming, it's VTH. Would take you less than 10 seconds to switch and take that measurement. Once that measurement is done, this is what you're going to do. On the left-hand side, you have a voltage source on that circuit. You're going to disconnect that voltage source from the circuit, and the circuit, the place in the circuit where the voltage source was connected, you're going to place a short circuit wire. And then you change the meter to measure resistance. Again, it should take you, takes less than like 30 to 40 seconds. And then so less than 2 minutes, you're done with all three measurements, but only if you do it in this order. Measure IN first, then measure VTH, then measure RTH. If you have done these three steps correctly, then you'll be done in less than 2 minutes. And then you keep the circuit as it is because you're going to use that entire circuit as a single resistor. Okay, so that circuit is made up of 4 resistors. You're going to use those 4 resistors as REQ, as one single resistor for the next 2 steps or the next 2 procedures. So keep the circuit as it is. Okay, and that's the lab. And then you're going to do some manual measurements using RTH versus RL and maximum power transfer theorem. Okay, read through the lab manual. There's only 2 or 3 pages for every lab, but it contains all the background information, and it also contains all the equations you need to solve the pre-lab. Okay, so again, if you're taking only the lecture, review the lecture videos, get started on the homework, at least get done with the tutorials if you can, and then bring your questions on Monday. And if you're taking the lab, then you have the lab notes here too. And then you have the lab pre-lab video also. You can go through that too. All right. So if there are no more questions, then we'll end class here today, and I'll see you all on Monday for mesh current analysis.